Turns out the universe has a problem, but in fact it doesn't. It's us that's got the problem. Everything we know tells us that there should be equal amounts of matter and antimatter, but there isn't. But if you're going to understand why, you need to create antimatter, and that's why you come here.
The Antimatter Factory is part of CERN, the European Centre for Nuclear Research. But before we go in, a bit of background. Everything we can see, touch and feel, and the things we can't see, like microbes and atoms, are all made of matter. It's what builds reality. And even though it sounds like science fiction, antimatter is also real, created in the Big Bang at the same time as matter. It's like a mirror image of matter, where the charges of its constituent particles are reversed. For example, antihydrogen has an antiproton with a negative charge instead of the positive we're used to, and an antimatter electron, or positron, which has a positive charge. When matter and antimatter come into contact, the two annihilate each other with a relatively huge release of energy described by this famous equation, developed by this guy.
So we've got a problem with the universe, Michael.
That's right.
What is it?
It's not empty. It should be empty. For everything we know, when the Big Bang turned its energy into stuff, equal amounts of matter and antimatter should have appeared. A particle is always accompanied by an antiparticle when it pops out of energy. E is equal to mc squared. And so you expect half of the universe to be matter, half the universe to be antimatter, and nicely mixed. When matter and antimatter meet, they annihilate, transform back into energy. So what you should expect are sort of islands of matter, islands of antimatter. And if you look at the universe right now, there is no antimatter. There are no islands of antimatter. There are no pockets of antimatter. There is no antimatter whatsoever, which means that what I just told you is completely wrong. That's not what happened. Something else must have happened at the beginning, which is that there's a slight imbalance in the amount of matter and antimatter that were produced. Maybe a little bit more matter than antimatter, so that all the antimatter and a little bit less than all the matter annihilated with each other. Those were the annihilations that I talked about before. But then because a little bit more matter was produced, that's what's left over. And everything we see in the universe, the clusters of galaxies, the stars, us, are the leftovers from this initial cataclysm.
So these days, antimatter occurs only very rarely in nature, created by lightning, cosmic rays, or radioactive decays. Even then, it only lasts for tiny fractions of a second before it comes into contact with normal matter and annihilates. So to study it, first you need to make it.
Hydrogen is the most common element in the universe, the simplest thing. It's the only antimatter atom that we can conceive of building. And we learned back in the early 2000s how to put it together here in this building.
The production of these anti-atoms begins at another CERN facility, where a beam of hydrogen protons is fired into a block of the metal iridium. The resulting collisions create many high-energy particles, including antiprotons. The Antimatter Factory's antiproton decelerator captures a fraction of these antiprotons and focuses them into a beam, while strong electric fields slow them to around 1/10 of the speed of light.
So we are here on the antiproton decelerator.
Right here,
Yes,
inside this white line.
exactly.
Oh my goodness.
Currently, there are 5 teams researching the different properties of antimatter. Professor Patrice Perez leads the G-bar experimental team, or gravitational behavior of antihydrogen at rest.
So the particles are running below you,
Yes.
and we are shielded against them because they could hit anything and produce particles which will be damaging.
Oh, so this whole hall is surrounded by the antiproton decelerator. I
Yes.
didn't understand that.
Yes.
So everywhere I see this concrete,
Yeah.
there are protons flying around behind it.
Yes.
And the concrete protects us from...
From the annihilation of these antiprotons with the vacuum tube which is keeping them. So if they interact, they produce secondary particles, and if there would not be the shielding, they would hit you and damage your brain, your cells, and it would not be good for your health.
And there's yet another decelerator, known as ELENA for extra low energy antiprotons.
So this is ELENA, which is a further ring to decelerate antiprotons. And there they are further decelerated to lower energy. And so this is nice to see because you can see most of the components which are also used in the big accelerator of CERN, the LHC.
Right.
But here we do the opposite, we decelerate.
You're slowing things down, not speeding them up.
Yes. The whole thing, the 80 plus this takes about 2 minutes.
Right.
So it's quite a long time for particles.
Yes.
And then they are extracted on this line, on this straight line, towards our experiments.
But before we follow those antiprotons through the Antimatter Factory, it'll be helpful to consider the scale of what's happening here. Let's begin with one we can easily understand, that of the human hair. An individual hair is 100 micrometers, and a micrometer is a millionth of a meter. At the level of individual hair cells, we're beyond the resolution of our eyes at around 10 micrometers. As we travel ever inwards, we soon cross the boundary where the human imagination starts to get a little blurry. At the level of atoms, we're measuring in picometers or trillionths of a meter. Beyond the electron orbitals of an atom, we still have a very long journey before we reach the nucleus and its component protons and neutrons, measured in femtometers, or 1,000th of a trillionth of a meter.
This is such a treat. We're right down in the heart of the experiment, but I think it's going to be a bit noisy.
To understand how matter and antimatter might differ, you need more than just antiprotons. You need anti-atoms, in this case, antihydrogen. Each experiment within the factory takes a slightly different approach to its creation.
So we are preparing this experiment. It's not yet running. So we are preparing to make first antihydrogen. We hope to do it this year.
Yes.
By merging anti-electrons called positrons with antiprotons, the one coming from ELENA. So we prepare these anti-electrons through this building. Inside this big building is hosted a small electron accelerator. This accelerator produces, converts the electron into positrons.
Positron is an anti-electron.
Exactly.
Right.
So we meet this anti-electron with an electron.
Yes.
To make a pair called positronium. So it's an anti-electron with an electron. They bind together, form a special atom called positronium for a very short time, 142 nanoseconds, and they form a kind of cloud of this positronium strange matter. And during this time, we shoot the antiprotons through, and the antiprotons catch two positrons.
And that makes a charged antiparticle.
Exactly.
This system is charged because the positive charges of the two positrons outnumber the negative charge of the single antiproton, creating an overall positive charge.
And because it is charged, first we can manipulate it more easily than a neutral one, bring it to a special place where they will meet beryllium plus ions.
Right.
Beryllium plus. So it's ordinary matter ions, which we also know how to manipulate with lasers.
Beryllium is the metal of choice because it's light, almost as light as the antihydrogen ions themselves.
We bring them together. When they are together, the lasers cool the velocity of the beryllium plus, which transfers this cooling to the anti-ion.
Right.
So it's a way to transfer cooling. And then when it is really cool, we use another laser, which take out one of the two positrons, then becomes back neutral.
Oh, so then you've got antihydrogen again.
Antihydrogen, neutral, and very cold.
Right. And what are you wanting to test with the antihydrogen that you create?
So with the antihydrogen we create, we want to check how they behave under the force of gravity.
Right.
The gravity due to the Earth.
For the G-bar team to be able to do that, the antihydrogen must be cooled by the beryllium ions to a temperature not exceeding 1/1,000,000th of a degree above absolute zero, or minus 273 degrees Celsius.
I'm really struggling with why you need to get it to 1/1,000,000th of a degree above absolute zero to check its relationship to gravity?
It's because when it is so cold, then it means you can think of it as having a very low velocity, like less than a meter per second velocity. Then it flies over a meter over a second, which means your apparatus is quite small, well, size of the meter. And then the free fall itself, you let it drop several tens of centimeters. So it's very simple to see. You can see a drop of 20 centimeters, and it lasts a fraction of seconds, not nanoseconds. Very easy to
But
detect.
you're almost getting it onto human scales.
Yes, exactly,
Right,
exactly.
right.
Inside CERN's Antimatter Factory, before Professor Jeffrey Hangst and his team can study antimatter, they need to make it, in this case, antihydrogen.
So we get a cloud of positrons, which we produce from a source, a cloud of antiprotons, and we coax them together very gently. Remember, we're trying to make something that's cold. That means it's not moving very much. On the atomic scale, we have the antiproton, which is the nucleus. The positron gets captured, they attract each other, and now we have an antihydrogen atom, which is neutral. No net charge, right? Of one negative charge, one positive, it's neutral. But it's a little bit magnetic. And so this magnetic configuration makes kind of a bathtub to hold the antihydrogen.
That's the magnetic field.
That's the shape of the magnetic well that
Right.
they're trapped in. In order to hold on to it, it has to be extremely cold. And by cold, I mean 1/2 of a degree above absolute zero.
And that means so it's really slowed down. It's not flying all over the place.
That's right. That temperature in this case is a measure of the velocity, of the motion, right? So we're essentially making a very dilute gas of antihydrogen atoms that are confined in a magnetic bottle. Alpha is the only experiment that's ever succeeded in doing this. And it's taken the whole of my career to learn how to both produce antihydrogen and then to trap it so that you can study it, right? And that's what this is all about.
So that's the key thing. It's an atom. It's antihydrogen, not an antiproton.
Exactly.
Right.
The mirror image, if you will.
Right.
Or the evil twin, as I prefer to think of it.
I found this even more amazing than the incredibly precise experimental physics going on here. How does a person dedicate their whole working life to understanding the properties of something as ephemeral and elusive as an atom of antihydrogen?
The burning question is very simple. Do hydrogen and antihydrogen obey the same laws of physics? Right? We don't know. That's an experimental question. What motivates it is this elephant in the room, which is the observed lack of antimatter in the universe. We simply don't understand that. We don't understand why you and I are made of matter instead of antimatter. It should be possible to have a universe that's made of antimatter. Some reason the Big Bang took a left turn instead of a right turn, and here we are. Now, I'm not promising that any of the research here can answer that question, but it's clearly, if you can get your hands on some antimatter, you should take a good hard look at it. That's what's going on here.
And so what properties are you looking at in particular?
We have kind of a two-pronged approach. The first thing is about light. Atoms like to absorb and emit light of particular colors, right? The classic example is the sodium street light that looks yellowish because sodium likes to absorb and emit yellow light. Hydrogen has its own series of colors that it likes to absorb and emit. In this case, they're not visible light, but we know them very, very well, right? We've been studying hydrogen for 200 years. It's how we learn to do quantum physics, the hydrogen atom, right? So we understand the properties of hydrogen with enormous precision and accuracy. The whole goal of this experiment is to try to make the same type of measurements using the techniques that have been developed for atomic hydrogen to see if the numbers are the same. And it's only very recently that we've succeeded in doing that. In other words, shining a laser on antihydrogen to see if it absorbs the same color of light as hydrogen does. Okay? These are some of the best things we know in the universe. The most precise numbers you'll find in physics are related to atomic spectra, the energy levels, the colors of the spectral lines from atoms.
And so does it have the same spectrum as hydrogen?
So far, we're just scratching the surface here, but the first precision measurements of antihydrogen are made here, and they're only 5 years old. I've been in this for 30 years, and it's only in the last few years that we've actually done what we set out to do a long time ago, which is a very fundamental transition in hydrogen that we've done in antihydrogen as well. Now, to give you an idea, we need to be a little bit quantitative.
Yes.
Okay.
Yes.
If I just measure the light that hydrogen likes to absorb, and I talk about its frequency, I can measure that number to a precision of 1 part in 1,000 trillion. That's 1 in 15 zeros. So 1 part in 1,000 trillion, that's the precision in matter.
Right.
We're now within about a factor of 500 of that with antimatter. So about 1 in 12 zeros, okay? We still have a long way to go, but we've now shown that this is possible.
But you're only 3 zeros off, isn't that enough? You know?
No, I mean, this is an experimental science. We're obligated to do things as well as we can in matter before we say, okay, I think that's as good as we can do, and we hang up the...
But why? Why does it have to be that precise?
Because what we're looking for could be very small, right? If there is some difference, and no one's saying that there is, no one even has a great idea about what could be different, it hasn't been observed yet, and that means that it's not a very big effect, right? So to look for it, you need to go to the ultimate levels of precision.
So let me rephrase that. Whatever happened at the time of the Big Bang, that means there isn't any antimatter in the universe, could have been so small, you need these huge amounts of precision.
Or more accurately, it may manifest itself today as a very small effect. Obviously, it had a huge impact at the Big Bang, right? The current thinking is that most of the matter and antimatter annihilated, and what we have left is what's survived. So it's a colossal effect at the beginning, but it may only manifest itself in certain systems in the 16th decimal place, right? So that's what we're looking for.
But you're not just looking at the light spectrum, are you? You're also looking at something else.
We're setting up to look at something else, and a very interesting question, what if I have some antimatter and I drop it?
Right.
Okay. What does gravity do to antimatter? Anti-gravity is one of the science fiction staples, right?
Yeah, yeah.
The answer is so far nobody really knows. That's an experimental question that needs to be answered. Antihydrogen is perfect for this because it's neutral. It has no net charge. You may think of gravity as being a strong thing. To us, it's incredibly weak.
Yes.
And if you want to observe it at all, you need something neutral. Antihydrogen is stable, neutral antimatter. It's the only thing like that.
So when you get your antihydrogen and you drop it, what's going to happen?
I don't know.
What do you suspect is going to happen?
Most theorists will tell you that it's going to fall in exactly the same way as hydrogen. I can't emphasize enough that that's an experimental question, and it has never been done yet. Right, so we're hoping to be the first to do that, to actually release them and see what happens. But this machine is new. It's just been put together in the last couple of years. We had a long shutdown, we had COVID. This will be the first full year of operation with this machine, Alpha G.
So if you drop it and you find out that antihydrogen drops differently in gravity to hydrogen,
that would be a revolution, right? That's simply unexplainable by any current theory. Our machine is designed to be completely agnostic about which way antihydrogen will go, right? We have to enter this with no preconception because you'll measure what you think if you have a prejudice. So it's very, very important. Alpha is completely up-down symmetric, so that if in the 1 in a million chance there is repulsive gravity, we will see it.
So Michael, we're dealing with the subatomic, but everywhere I look here, everything is so big, it's so chunky, it's so industrial. Why is that?
Well, first of all, we need big equipment in terms of magnets, vacuum pumps. All the laser systems that we have here are like square meter sized. And so in order to get to these tiny little atoms, to be able to manipulate them, we need equipment that requires power, that requires fluids, that requires cooling. We need the big equipment to do the very small.
To mimic what the universe is capable of doing on its own.
Well, we're only making a single atom at a time. The universe was a little bit more efficient when it did that at the
A little
beginning.
more ambitious.
A little more ambitious, exactly.
Before we learn about the approach taken by Professor Dozer and his team, a bit of a warning.
Yeah, before we head into the zone, I need to warn you, there are quite a few hazards when we're running. We work with cryogenic liquids, we have very powerful lasers, strong magnetic fields in case you have a pacemaker. Of course, we're underground, so things can fall on you. There's overpressure. If our liquid nitrogen flows out, you can asphyxiate. It's very noisy, and of course, things can blow up. So just
Okay, so nothing
relax.
to worry about at all.
Exactly.
All
But
right.
we're not running, so all this is off.
Oh, okay, good. Thank you.
Yeah, so this is the experiment that I run.
Yes.
It's the Aegis experiment,
Yeah.
which
Aegis stands for what?
antihydrogen experiment, gravity, interferometry, and spectroscopy.
So I see behind us, it's looking a bit like it's in construction, is that right?
So it's not actually in construction, it's being refurbished partly. In 2018, we produced antihydrogen in a pulsed form, which was a new step for the field, because normally when you produce antihydrogen, you sort of pour the antiprotons into the anti-electrons, and then this soup then pops out antihydrogen atoms continuously. For our experiment, we want to launch the antihydrogen atoms. So we need to know exactly when we make the antihydrogen atoms, and we do that by holding antiprotons and shooting these atoms of an electron and anti-electron atom.
Remember, Professor Dozer is talking about those strange matter atoms of positronium that we learnt about earlier, made up of an electron and its opposite, a positron, bound together for a very short time.
And as they go over the antiproton grabs the anti-electron and forms antihydrogen. And this is a process that we can control to the nanosecond, to the billionth of a second precision. So we did that in 2018. The next step will be to launch it.
Yeah.
Because we would like to shoot it horizontally like cannonballs in a cannon and watch the parabolic drop of this antihydrogen. Exactly. So we're going to measure the drop. This is also why we need to know when we make them, because we are going to measure how long they have been dropping. The colder they are, the more they have time to fall. And gravity is this weird thing, because the more time you have, the better you can measure things. It's a quadratic parabolic trajectory. And so if you give them more time to fall, they will fall not only twice as far, but 4 times as far. Now, how to shoot them is something we're working on. We haven't done that yet. That's one of the things for this and next year. We want to make lots of antihydrogen. That's the program for this year. And then next year, work on that.
And when you shoot them, you're going to see if antihydrogen drops just as much as hydrogen does.
That's exactly the goal, yes. Now, we all expect antihydrogen to fall exactly the same way as matter. I think nobody really believes that it will fall differently. The sign is sort of not in doubt. And in fact, there are already indirect measurements that have shown that to a part in a million, a bit better than a part in a million, they will behave the same gravitationally. So what the long-term goal is, of course, is not just to do a measurement to a few percent or a few per mil, but to be more precise than these indirect measurements. So a part in a billion, for example. That's what we would like to do.
Why do 3 different experiments need to ask this question about gravity?
So first of all, because we don't know how to do the experiment. I think that's the bottom line. There are 3 different approaches that are completely orthogonal to each other. We don't know which one will work and which precision the different experiments will find. Now, that's the main reason. But there's a secondary reason, which is also why there are 2 big experiments on the Large Hadron Collider. And that is to, I wouldn't say keep each other honest, but to check on each other's results if something unexpected is measured. If you only see one signal in one experiment that is unexpected, you don't know whether it's an artifact of that experiment or whether it's the underlying physics. So you need to have another experiment that uses a different method to test and probe that result, confirm it or infirm it. Nobody has tested gravity directly. In a few years' time, we'll know, hopefully, that it's the same to a percent. but it might still be hiding at the per mil level, at the part in a million level, at the part in a billion level. And in fact, this is how all our knowledge is obtained. It's by expanding what you know, seeing that there is no difference or that everything conforms to expectations as precisely as you can, and then hoping that if you're more precise, you will see something unexpected, something that doesn't conform, something that infirms the standard model. And the standard model is incomplete. We already know that. There's something missing in many different ways. And what is missing may well have to do with gravity. If you think about what dark matter is, what dark energy is, the indirect signs often have to do with gravitational signals that one sees. So gravity plays a role in the unknowns, which is one of the reasons why we're so interested in exploring gravity here.
Oh, so it's not only telling you about antimatter, it's telling you about gravity.
Yeah, a little bit. If we see a difference. If we don't see any difference, then unfortunately gravity is still described by general relativity. Same old general relativity.
Right.
That works so well.
But if you did see a difference?
That would open up a door into a new direction, into a wider understanding of what the universe is, how it works, how its building blocks interact, what it's made out of.
So how precise do you want to get before you say that's it, we're certain now, there's no difference?
So before I give up, because I only give up if we don't see a difference, I would say I've got another 30 years of life ahead of me. By then,
more.
Maybe, well, I'm not that young anymore. By then, I hope to get to the level where we have a better precision here than with the indirect measurements. So a part in a million, a part in a billion, in that range. If we can get to that, I can lie down happily.
You can hang up your hard hat.
I can hang up my hard hat happily, yes.
When that happens, we'll be closer to understanding why we live in a lopsided universe where antimatter hardly exists. For now, despite all the discoveries of recent times and the amazing work accomplished in places like the Antimatter Factory, the one thing we understand best about the universe is how little we actually know.